Hello, good evening. Welcome everyone. Yeah, this is an extra session because exams are near. So um, this session will be mostly questions and answers, and to clear any doubts or any problems, any questions that you have. So we'll be discussing those things. Uh, we'll wait 2 minutes for uh, more people to join, and then we can start. In the meantime, if you have any questions, please let me know. Of like, it could be from any of the previous weeks, from week 1 to week 7, or even if week 8, like the whole course. Yeah, so Monica is asking, will they give coding questions for exam to write and execute the code? No, I don't. I don't think so. We won't have. We won't have to write and execute the codes, but you know, so it will be. I mean, the hands-on exercise that we did in the previous weeks, uh, those are actually essential for your future purpose. So, for example, you all are doing this course to get the certification, and maybe you are going to apply for internship or jobs in future, right? So, I mean, in those places when you are like doing internship or jobs, you have to write the codes, right? That's the practical objective, right? In the end, theory is okay, but you have to implement this algorithms, implement what you have learned to uh, to do your projects or anything, right? So that will help you in those parts, because doing this course and getting the certification after 1 month, you will forget everything, right? So I think those hands-on exercises are something that you should keep practicing, and that's why I keep uploading the notebooks and the codes that I discuss in the Google Drive. So I highly recommend that whenever you get time, try to go through those codes and see how it works, because that's gonna help you uh, later in future, when you will be doing projects on this, to basically implement this on in practical life scenario. Okay, so uh, Acha is saying explain binary classification problem, how to find entropy of data sets. Uh, okay, Prerna is asking explain back propagation training the algorithm and derivation. Right. Okay. So by binary classification problem to find the entropy of data sets, you mean in decision tree, right? And uh, how to find entropy and information gain and those things. Right. So there are okay. So I will do one thing. I will first do how to calculate entropy and information gain. That part I will do, and then I will explain the back propagation algorithm. Right. All right. So first, let's go to binary classification problem. Let me share my screen first. All right. I hope my screen is visible. Okay. So yeah, I can explain the binary classification problem with an example maybe. So yeah, before that, I hope you guys are familiar with decision trees. I'll just briefly explain what a decision tree is in a, in 1 minute maybe. So so decision trees are you know unlike uh, regression problems, decision trees follow a hierarchical structure, right? So if you see from here, so let's say you have some data set. First is goes into the decision node, right, root node, and then it goes into the further sub nodes. Right? So it branches out just like a tree. So this is the root, and from there it develops different branches, and finally it, it makes a decision at each of the nodes, and then finally branches out, and finally the end nodes, which has no other branches, are called leaf nodes, right? So, for example, it could be used for any real life problem. For example, if you want to determine whether a person is fit or not, so you have to check whether the age is less than 30. If yes, then you have to check whether he eats a lot of pizzas. If yes, then he's unfit, and if no, then he's not. He's fit, right? So similarly, so this is one of the basic examples, right? So okay, so right. Now, what we will do is we will try to see how to calculate entropy and information gain with the help of one example. Right. So, if you see here, okay, let me explain this one first. Okay. So first, this is the age. Uh, Okay, Srinivas Rao is saying explain decision assignment decision problem. Yeah, I don't. I can't. Can you elaborate a little bit? What do you mean by assignment decision problem? Okay. In the meantime, let. Yeah. Sorry. Yeah. Yes. Okay. Which assignment are you talking about? Assignment number. Okay. 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 Let me share my screen over here. You're talking about this problem, right? The question 7, 8. Uh-huh. Huh. So you want to know how to calculate entropy of the data set. So the first question you have to calculate entropy of the data set, and then in the second question, you have to calculate what is the information gain uh, of vaccination, right? Mm-hmm. Right. So question 7 you is you understood, right? Hmm. Right. So first, let me uh, do the calculation for entropy and information gain since someone asked. I will calculate it for one example and then I will come back to this and I will explain how you can apply uh, those calculations in this case, in this example. Okay. Okay. So first, let me look at this example. So this is the so you have like 5 data points in which you are given data of age. So let's assume that these 5 are 5 different cricketers, let's say, and their age is given, their weight is given, and the number of injuries they had is given. Now the results indicate that whether they are being selected in the team or not. So, for example, if the result is 1, that means they are selected in the team. If the result is 0, that means they are not selected in the team, right? So, you have to make a decision tree in which uh, you have to see whether, so basically, you give an input and your input of any player data, and the decision tree will tell you whether that person is selected or not, whether the result is 1 or 0, right? So that is the problem statement, right? Now, sorry. Now, uh, let's assume that you make this kind of a tree. Okay. So your tree first node is age less than equals to 30.5, number of injuries is less than equals to zero point 0.5, right? So if age less than 30.5, if that's true, then it goes into this node, right? So age less than 30.5 is true for this one, right? This one, sorry, one, two, three, this three, basically, right? So, so 3 people are going into this node. So if you see, 3 people, samples is equals to 3, right? Initially, you have total 5 samples, total 5, out of which 2 are negative, 2 are basically 0, 2 has result 0, 3 has results 1. And in this node, there are 3 samples, out of which 2 have result 0 and 1 has result 1. And then you further branch it out. And if number of injuries is less than zero point 0.5, that means number of injuries is 0. So in this case, this one. So only this one is coming into this node, right? So basically there are no zero values and there is one value with result one, right? Similarly, this is the tree that you have formed. Now we have to calculate what is the uh, initial entropy of the tree, right? And not only initial entropy, we'll calculate entropy at each nodes, right? What is the initial entropy and what is the entropy after this node? What is the entropy of this node? We'll do it everything, right? And finally, we'll see what is the information gain that has been achieved by adding this node and then adding this node. Any node you take, we can uh, we can basically calculate the information gain of each and every node, right? We'll see how to do that. Okay, so let me go back to my whiteboard and let me see. Okay, let me open this one. Okay, so this is the tree, the exact same tree that I showed in the slide. Just I have redrawn it. So age is less than 30.5 is the first card. And then we go into this injuries, number of injuries less than zero point 0.5. If true, then we are saying that, okay, the result is 1. If false, then we are saying result is 0. And again, if at the initial stage it satisfies that age is greater than 30.5, then we are saying that the result is uh, 1, basically, right? So in this node you have two samples with value 0, one sample with value 1. In this node you have 0 samples with value 0, one sample with value 1. In this node you have two samples with value 0, 0 samples with value 1, and so on, right? Now the formula for entropy is this thing, this one given over here, right? So this is I'll just explain what it says. This is negative of probability of positive log 2 probability of positive minus probability of negative log 2 probability of negative. Now if you want to calculate the initial entropy, which is the entropy before making the tree, so in the total samples you have like 5 samples, okay, and out of which 2 are value 0, 3 are value 1. So what is the probability of the sample being positive? So being basically results equals to 1, probability is 3 out of total, 3 by 5, right? So your P plus would be 3 by 5. So that's what is calculated over here. This is the root node entropy that I'm calculating. So minus 3 by 5 times log base 2 of 3 by 5, right? And similarly minus P minus, what is the probability that result is 0? So that is 2 2 by 5, right? So 2 is 0, 2 samples is 0 out of 5. So 2 by 5 log 2 times 2 by 5. If you calculate this, you'll get this value 0.97. So that is called the root node entropy. I mean, before you begin the tree, at the root node, this is your entropy, right? Similarly, similarly, you can calculate the entropy at each nodes, right? In the assignment question that we just saw, they have asked us to calculate the initial node entropy, but in the exam they can ask you to calculate, so in this injuries, right, and so on. So if they ask you to calculate what is the, would be 1 by 3, because there are 1 samples which are positive and 3 samples total. So minus 1 by 3 log 2 1 by 3 minus P minus 2 by 3, right? So minus 2 by 3 log 2 2 by 3, right? I might just write it down if you want. Okay, so right. So entropy. So before that, your P plus is, sorry, 1 by 3. P minus is 2 by 3, right? So from the formula, if you see the entropy, so right now I am calculating entropy for this node. Remember this node. So in this node, you have two samples with values result 0, one sample with result 1, right? So actually, yeah, uh, entropy for this node is minus 1 by 3 log 1 by 3 minus 2 by 3, and all logs are base 2. Okay, 2 by 3, right? Similarly, you can calculate the entropy for this node, right? And entropy for this node would be 0, because you see the okay, let me calculate it. Entropy for this node is, so let me call this node something. Let me call this, call the first node as A, this node B, C, D, and E. Okay. So entropy for B is this. Entropy for C would be, if you see the probability of plus is 2 by 2. 2 by 2 is 1. 1 log 2, 1 minus 0 log 0. So 0 is this, this becomes 0. So this cancels. And 1 log 1 is 0, right? Log of 1 is 0. To calculate what is the, so root node, so initial entropy is obviously, as I calculated here, 0.97, right? Now, what is the entropy that this node has? That is this thing. You have to calculate this, and the entropy of this node is 0. Now the question is coming to the second part, which is information gain, right? So what does information gain mean? Information gain means that uh, what is the gain in information that you have uh, by making this cut using age variable. So how much information this age variable is adding to your model, right? So instead of randomly uh, classifying samples, what is the significance of this age variable? So that is the question. Okay, someone is asking, we can take either of 0 or 1 as positive or negative, right? Uh, yes, you can, because this formula is symmetric about. Uh, I mean, this form, the total sum will be constant, but generally people take uh, 1 as positive and 0 as negative. But yeah, ideally the value would come out to be same, right? There is, you can do that. Okay. Now coming to information gain. So okay, Prerna is asking leaf node. Yeah, C is also leaf node. But you see, if if it's a leaf node, uh, I mean, doesn't necessarily mean that entropy should always be 0. Um, okay, because you see in this leaf node, you have is the screen sharing off in YouTube? Okay, let me share it again. Yeah, thank you for pointing it out. Thank you, Satish. Yeah. So, yeah. So, as I was saying, that in this case, the leaf node entropy is 0, because in the leaf node, you have all the samples in one category, either they are positive or negative. So there are no so in this case, let's say in C node, there are no samples in with result 0. There are only samples with results 1. There are two samples with results 1. So that's why your leaf node entropy is 0. But if there were some samples with result 0, then the leaf node entropy would not be 0. So for entropy to be 0, simply you can remember this: entropy is 0 when that node has samples only in one category, like either they are all positive or all negative, right? That's the basic rule that you can follow. Okay, right. So in this case, all the leaf nodes has samples in only one category. So that's why in this case, all leaf nodes have entropy 0. But in a very general case, that might not be true always. Okay. Right. So yeah, that means leaf node is not always 0. The entropy is 0 only when all the uh, samples belong to a single category. Right. Now I was talking about information gain, right? So yeah, I think I had written this, that information gain means the percentage of importance of that cut, or that of that node, right? So for example, what is the importance of age, right? So information gain of age. So that's what you calculate over here, right? So how do you calculate this? So you see that initially your initial entropy was 0.97 that we calculated earlier. Now we want to see what is the reduction in entropy by adding the node age, right? So initial entropy was this. Now what is the entropy after I have added the node age? So the entropy would be, so for this node, as I said, the entropy was 1 by 3 log 2 1 by 3 and minus, that will come out to be 0.92, right? So this entropy B. So if you calculate this formula, it will come out to be zero point 0.2, right? If you just calculate using a calculator, right? So now it will come out to be 0.92, right? And this has entropy 0. So now we want to look at the just the subnodes of age, right? So the subnodes of age are B and C. So we want to see. So if you see the formula, gain is given by entropy of the previous node. I mean, that is the root node, 0.97 minus Now you have to see. Now you have to weight the uh, entropy of each nodes B and C. So what is the weightage of B node? How do you calculate weightage of B node? The weightage of B node would be the number of samples in the B node. Number of total samples doesn't mean 0 or 1, right? Total samples is 3. 2 or 0, 1 is one sample as value 1. So total sample is 3 divided by the total number of samples of all the nodes, like both B and C, right? So the total number of samples of B and C is 5. So 3 by 5. That's how you weight. That is the weight of basically node B. So 3 by 5 times the entropy of node B, 0.92. And now again you have to do this. Okay, this I have not done because the value is 0. So now here what you have to do, you have to basically also subtract out the entropy of C node. But here the weight will be 2 by 5 times, but entropy of C node is 0, right? So that's why I have not written this part. So this will become 0. So you just have to calculate the entropy gain. Okay, I've written it actually below over here, right? Okay. So yeah. So yeah, so that's what I was saying, that you have to subtract the entropy of the subnodes of node B and C from the root node, and you have to weight them by their sample numbers, and that is the information gain that you calculate over here. That is 0.418, right? So that's how you get it. Now, Is there any question? I mean, did everyone understand the calculation part? Okay. So as Srinivas was saying that the initial entropy that you can calculate simply, right? That's just p plus minus uh, minus of p plus log p plus minus of p minus log p minus, right? So you have to see how many samples are plus and how many samples are minus. So there are like I guess how many samples are given? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 12 samples are given total, out of which 5 are 1, so 7 are 0, right? So p plus would be 5 by 12, p minus would be 7 by 12, right? Simply you can do that. Okay. And for the uh, okay, for the next part, what is the information gain of vaccination, right? So yeah, uh, so basically, what you have to do, you have to uh, make a tree whose node will be vaccination, right? So, and now you have to see. So, if vaccination is one, if vaccination is yes, then within that, how many? So, let me do it actually. So, what I'm trying to say is, so so you make a tree which has vaccination as the node, and if vaccination is yes, so initially you had 7 zeros and 5 ones, so total 12 samples, right? So initially your entropy would be minus 5 by 12 log base 2 5 by 12 minus 7 by 12 log base 2 7 by 12. Now someone calculate and tell me what is the answer. I know it's given in the assignment probably, but uh, well, let me check it from there. So I hope the this comes out to be 0.9798, right? So I'm not calculating this, but can anyone verify that you get this by calculating this, right? Okay. So if vaccination is yes, so I will see what are the how many samples have vaccination yes. So I'll only look into those samples. So first I am looking into this branch, right? So now if I'm looking into this branch, so you have this sample, both are zero, this one is zero, so three zeros, four zeros, right? Five zeros, right? So you have five zeros in this branch and no ones, right? Whereas in the case where vaccination is no, so this have you have this case which has zero, one zero, two zeros, okay, two zeros and five ones. So total seven samples in those. Okay. So what I'm trying to say is that if vaccination is yes, then you have five cases which do not have malignant tumor, and zero cases which have malignant tumor. And if vaccination is no, you have two cases with no malignant tumor and five cases with malignant tumor, right? So now, how do you calculate the information gain? So again, we'll just use the formula. So the initial gain 9798 minus uh, minus we have to first calculate the entropy of this node. So if we calculate the entropy of this node, so again, as I was saying, if one node has all the samples in a single category, that will have entropy zero, right? So this node has all of them in single category, so entropy equals to zero. But we have to calculate the entropy for this node. So entropy for this node would be 2 by 7 log base 2, 2 by 7 minus 5 by 7 log base 2, 5 by 7, right? So you have to calculate this, right? And then coming back to this formula, okay? So let me calculate this first because we will use this. Okay. If anybody knows the answer, please let me know. Also, make sure to take the logarithm in base 2. Okay, so that is important. Don't miss that while you are calculating in a calculator. Because in general, in a calculator, the base is basically E, right? So be careful about that. So the first part is 0.52 plus the second part would be 0.35. So it will be 0.87, right? So, okay. So the gain would be, uh, again, the weight of the first node. Again, let me call this A, B, C. So the weight of B node is basically 5 by 7, but entropy is 0. Sorry, 5 by 7 plus 5, that's 12, right? And the weight of the C node is 7 by 12 times entropy of C node, which is 0.87, right? So again, let me calculate this thing. So it comes out to be 0.4723, something like that. I made some round offs, but the answer should be closer to this. Yeah, 0.4763. So this should be the answer, right? Yeah. A. Yeah, I made some, round offs to two decimal places in between while I was doing the calculations. So if you see 0.87, so there are like further digits over here. So that's why I got 0.4723. But if you do the actual calculation, like taking till four decimal places, you will get this. Okay.
So thank you.
Yeah. Thank you. So this is how you do the entropy and information gain problems. Anybody else has any question on this part? Okay, I guess Prerna has asked about the back propagation training algorithm and derivation. Uh, so before that, if anybody else has any question on decision tree, we can discuss that now, or we'll move into that. Right. Okay. Prabha is asking, do you have negative marking? Yeah, I'm not sure for the final exams. Uh, I think that is something the professor would know because I'm not setting the question paper. And anyway, it will be written in the instructions for sure. But for any exam related doubts, I think it would be better if you ask uh, in the question and answer forum. But generally, uh, in this kind of courses, they don't have negative marking. So uh, generally, you can be assured of that there will be no negative marking. But still, you can ask it in the Q&A forum of the course. Okay. Now, for back propagation algorithm. Okay, so I'll explain forward propagation as well, and then I will explain back propagation and how to derive this. So, so I'll explain with an example, and so here, uh, like you have dosage of some medicine, okay, and it just means that this is the low dosage, and this is as you increase going the x-axis, this is high dosage, right? And this is the medium dosage, the this one, because this is something at zero point 0.5. So this one has dosage value equals to zero point 0.5, this one has dosage value equals to 0, and this one has dosage value equals to 1. So what this means is that if you have very low dosage, the medicine doesn't work, right? So basically, it's a medicine that you are taking, let's say, and if you are taking low dosage of that medicine, that doesn't work. So that's why the result is 0. If you take medium dosage, then it works. The result is 1. Also, if you take very high dosage of the medicine, it doesn't work. So the result is again 0. Right. So if you know about you know neural networks, right? So I think we discussed it in week 6. So these are the structures of neural networks. So actually, if you go back, so these are some, this is the structure of a perceptron, right? And then we discussed how we can build logic gates using perceptron. So these are actually very important. I think, I mean, you can expect at least one question from this logic gates. You might be asked to calculate these weights, you know, given a logic gate, or you might be asked like, given the weights, what is the logic, what this logic gate would be, whether this be or gate, and gate, NAND gate, NOR gate, right? So yeah, that is one important point. But again, that's a we had done it in week 6. But right now, let me explain the forward propagation thing. So these are neural networks which are made of perceptrons, and this is the simplistic form of a neural network that I can draw for this data that I have. So this is the input layer. The in between you have some hidden layers. So here I have taken only one hidden layer, but there could be multiple hidden layers in practice. And then you have output layer, right? So again, there could be multiple hidden layers, and there could also be multiple, these nodes in this hidden layer, multiple neurons in this hidden layer. So here I have just taken two neurons, but in practice you can have multiple as well. But to understand or to explain, I think this is the simplistic model, and we can use this example to understand this. Okay. Okay. Ramesh is saying you're not able to see the shared screen. Is that right? Uh, Everybody else?
Most of it is
Yeah. Okay. Okay. Yeah, I guess that might be some problem on Ramesh's end, but yeah, I think everybody else can see it. Okay. Thank you. Thank you. Right. So yeah, so let me explain forward propagation first, and then I will explain backward propagation. Now, uh, you see that basically your problem statement is you give an input of dosage to this model, and the model will give you an output. So you expect that if you give the input as zero over here, that means zero dosage. That means your output should be zero because that the medicine won't work. Whereas if you give very high input, like let's say input one, so then also your output would be zero. And if you give medium input, medium dosage, that is zero point 0.5, your output should be 1. So that's what you expect. That's what you want, right? Now, you get these weights. So the way this you get these weights is through back propagation, that which I will explain after this. But let's assume that you get these weights through some method, right? Through back propagation, and you know these weights are this thing. Now, how does this function, right? So if you let's say input 0 over here, your input will be multiplied by this weight w1. Let's say this, let's call this w1. So input is 0, 0 times 3.34 plus this is one bias. So whatever the multiplied value will be added to this value. So, and then it will be passed through this activation function. So this is an activation function. So I think you guys are familiar with it. This could be a sigmoid function. This could be a ReLU function. This could be a, 10H function, or soft mass function, or soft plus function, or anything, right? So this output, whatever the after the multiplication and the addition, whatever value you get, right? So if the input is 0, 0 times 3.34 is 0 plus minus 1.43. So the value would be minus 1.43. And this value you pass through this function. So whatever the function, if the x value is minus 1.43, your output would be something very close to 0 actually. Okay. So you get the output from here after passing it through this function, multiply it with this, right? And similarly, if you do this on the bottom layer as well, right? So bottom channel, I would say. So in the bottom channel, whatever you get, so after multiplying with this, in the bottom channel, you have different weights, okay? So in the top channel, you have different weights. In the bottom channel, you have different weights and biases. And finally, whatever the value you get from here, you sum it up with the bottom channel, and then you add the final thing with this, right? And then you get the output, right? So again, if I just show you, if you input 0 over here, you would get a value very close to 0, right? So that's what you will get. So let me, I think I have some notebook already where I have calculated this. Possibly it's in week 6. Okay, this is the notepad. Right. So I have drawn the same tree over here. So input you take as 0, multiply it with 3.34 minus 1.43 bias, and you pass this 1.43 to this, sorry, minus 1.43 to this soft plus function. The soft plus function is log of 1 plus e to the power of x. So log of 1 plus e to the power of minus 1.43, that will give you a 0.22 value. You multiply the 0.22 with minus 1.22, you get minus 0.27. Okay, similarly, you do this for the bottom panel, you get minus 2.35. You add minus 0.27 and minus 2.35, and then you add the 2.61, and then you get a value of minus 0.01, which is very close to 0, right? Similarly, you can do it for an input of zero point 0.5. If you do it for an input of zero point 0.5, you should get a output very close to 1, right? Because for a dosage of zero point 0.5, your medicine works. So your output should be 1. Okay. Okay. Kavita is asking to explain once again. Okay. Okay. Let me go back one step. So here you see. So this is the neural network. So that's exactly what I have done. So first, I give the input as 0, multiply it with 3.34 plus minus 1.43. Whatever the result I get, I pass it through this soft plus function. The soft plus function is log of 1 plus e to the power of x. The x value would be basically this, whatever the summation I get. So here, if I multiply it with 3.34 and add it with minus 1.43, I get minus 1.43, and I pass it through this soft plus function. So this is where I am passing it through the soft plus function. Log of 1 plus e to the power of this value, right? So you again use a calculator to calculate this. You get 0.22, right? So after passing it through this function, you get 0.22. Now you multiply the 0.22 with this thing, minus 1.22, right? So that's what I have done. 0.22 times minus 1.22. You get minus 0.27. Okay. So you get minus 0.27. Similarly, you do the same thing for the bottom channel. So you multiply 0 with minus 3.53, add it with 0.57, right? Okay, what is minus 1.22? Okay. So, right. So these are called weights, right? So if you remember, if we go into the perceptron model, what we used to do. So if you remember this thing, so these are the basic frameworks of the neural network, right? This perceptrons. So how do we calculate this thing? So what happens is that you get the input, you multiply it with the weight, right? Similarly, you multiply other inputs with weight, you sum it up, right? You sum. This is the summation operation that is happening. And then you pass the summed value through a activation function, and then you get the output, right? So same thing we are doing over here. So we are multiplying it with weights, then adding a bias, passing it through the activation function, right? And then again doing the same thing, multiplying it with weight, and we're doing the bottom layer as well, and then summing it up, finally the output. Srinivas is saying, shall we add bias for each input? Yes, you should add bias for each input. For yeah, for all the layers. Like the bias could be 0, right? But the question is, how do you decide what is the value of the bias? That I will explain in the next part when I'll explain the backpropagation. Like, how do I arrive at this value minus 1.43? Why not some other value, right? Okay, so that I will get into the next slide. So the bias value could be 0 as well. In that case, you will have no bias. But in general, this is for the most general case. In general, you will have some bias, right? So again, to answer Kavita's question, these 3.34s, yeah, sorry. Yeah. So whatever values you are multiplying, those are the weights. And whatever values you are adding, those are the bias. Simple. It's as simple as that. Right? Yeah. Okay. So yeah, is the forward propagation algorithm clear for everyone? I mean, Yes. So whatever the formula is for the sigmoid function is e to the power x divided by 1 plus e to the power x. So like this here, uh, here if you see this minus 1.43 value that I have passed through the soft plus function. The soft plus function is given as log of 1 plus e to the power of x, right? Similarly, the sigmoid function I believe is given by 1 by 1 plus e to the power x. Okay. So similarly, what you do is if you use the sigmoid function as your activation function, let me go to the slide now. Okay. Okay. So uh, you see here minus 1.43, you are passing it through the soft plus function. If you are using the sigmoid function, which is given as sigmoid function is given as 1 divided by 1 plus e to the power of minus x, I believe. Okay. So here the output would be 1 divided by 1 plus e to the power of plus 1.43, right? So you just calculate it over using a calculator maybe. So let me see, 1 divided by 1 plus 2 to the power of 1.43, right? So this will come out to be around something 0.19, right? If you use a calculator, this will come out to be 0.19, right? So, so instead of this 0.22, now we'll get 0.19, right? And then you repeat the same process again. Okay. So that is, yeah. So that is what will happen. Similarly, you can take any function, not necessarily sigmoid. So whatever the form of that function, that will modify this accordingly. Okay. For softmax, I believe it is uh, e to the power of x by 1 plus e to the power of x, I think. Yeah, something like this. For softmax, I think e to the power of x divided by 1 plus e to the power of x. Okay. Sorry. Actually, log of that is soft plus. Okay. Okay. So there are like lot of activation functions that are being used. So this is sigmoid. Okay. Then ReLU would be, it is basically zero for anything less than zero, and for greater than zero, it is x. So it is a function zero if x is less than zero, and x for greater than zero, right? Now the sigmoid I have told soft plus activation function is given by log of 1 plus e to the power of x, right? And this is soft plus this e to the power of x divided by this is soft max, sorry, soft max, right? So sigmoid, ReLU, soft plus, soft max. I think there are many other activation functions as well, right? So yeah, you can like look into all those. Those are different functions, but these are the pretty much most basic ones. So I guess you don't have to memorize. I mean, some of them you can memorize, like sigmoid, soft plus, ReLU, and softmax. These four you can memorize. I think the rest are not so commonly used. So these are the ones which are most commonly used. Sorry. Yes, yes. So also that depends on the problem as well. So if some particular activation function is giving you better accuracy or not, so that you have to see, right? So also, like, you have to see, like, so for example, uh, you know uh, this sigmoid function, so these can only take values between 0 and 1, right? So if you remember the sigmoid function, this will give you value only between 0 and 1. So also it depends on your problem. So if your problem has a multi-class classification problem where you need values which are even higher than 1, right? So for example, you are classifying a three class problem where your results are 0, 1, or 2, right? So sigmoid function cannot give you value 2. So in that case, you have to use some other activation functions, maybe ReLU or something else, right? So these are some of the things that you have to keep in mind while using these activation functions. But in general, for binary classification problems, you can use all of these as well. I mean, you can use any of these, but these are most commonly used in practice. But there are a few uncommon activation functions as well. But you have to see, like, the choice, like which one to use in for the particular problem. That depends on the problem. And again, so there comes like cross validation. You can use different activation functions different times, and then you can check which activation function gives you the best accuracy on your cross validation data set or testing data set, and so on. You can do that, and that way you can check which is the best activation function for your problem statement. Okay. Okay. So I guess forward propagation is clear now. We'll now move to backward propagation. Okay. So basically, yeah. One thing is that this is a very specific example, but as I said, in general, you can have multiple neurons and in a layer, and you can have multiple layers, but all these layers and all these neurons will basically function in the same way. Like, they will have their separate weights and separate biases. For example, if you add another neuron on this layer, like over here, that will have a separate weight and separate bias, and then again a separate weight, and then the three will add together and then give you the output, right? So in this way, you can, like, add more and more neurons, and finally you can also add more and more layers and build a complicated neural network, right? But this is the idea. This is You can generalize this idea to more and more neurons and more and more networks. Yeah, Ramesh has raised a hand. Is there a question? Okay. If not, let me go to back propagation. So in back propagation, we'll use something called chain rule, which I discussed in the previous class. So tell me if I need to discuss it again, or I mean, I can discuss it again if you want. Let me go to here. Okay. So I think with examples, the chain rule would be uh, pretty easy to understand. So, for example, if you have some function y, which is a function of x basically, but it's a complicated function of x. So e to the power of ax square, right? So it's a very uh, complicated function of x, not a trivial function. So everybody here is familiar with differentiation, right? So do I need to explain what are derivatives and all? Like the differentiation of basic functions like e to the power of x, uh, x square, and log x, maybe sin x, cos x, and those functions. Is a like you can tell me if you are not familiar, then I can just explain in a minute. Okay. Okay. So I assume everybody is familiar with that. So okay. So yeah. So for example, derivative of x square is 2x, right? So and yeah. Is there a question? Uh, okay. So I think Ramesh is asking that in the block diagram, it is shown that one of the values are passed on to the activation function. The output is calculated, but in the example, it shows that again some calculation function is performed before getting the output. Like specify in which case you're talking about. I don't. If you can like talk in the mic, then microphone, then I think it's better. But so I think you're talking about the algorithm. Yeah, which part you're talking about? So we do this calculations over here and pass it through the activation function. Like after whatever the result of this calculation, and then the output of the activation function is then multiplied by this value, and then sum it up with this, and then finally we get the final output. So I didn't get which part you are talking about. Yes. Yeah. Yeah. Sure. 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 Yeah. So derivatives are basically, you know, that means taking the slope of a function, right? So any function you have. So by function, what do I mean? Is that uh, you know it could be any function of x. So let's say uh, you change x. So x could be, let's say, your length of the house, right? Whereas fx could be your area of the house. So as you increase the length of the house, right, your area also increases, right? And it increases like area equals to length square, right? So increases in a square way, parabolic way. So if your length is 1, your area would be 1 square, that is also 1. If your length of the house is 2, your area would be 4, 2 square, area of the house, right? Simply like that. It could be any function. So any function of uh, any variable could be this fx, right? That could be represented as a curve, right? So now here I've given a simple function like area and length. You could have any complicated function of anything, right? Any complicated curve like this, okay? Right? So now derivative is just the slope, right? Simply uh, the slope of the curve at any point. So let's say if you want to take the slope of this curve at this point, right? So if you see the red curve, right? So I want to take the slope of this curve at this point. And by slope, what do we mean? That how fast fx is changing if we change x, right? So here you see that it's changing in a square way. So if I change x from 1 to 2, fx is changing from 1 to 4. If I change length from 1 to 3, the area would change from 1 to 9. So this rate, right? If I change x by some amount, what is the amount by which fx changes? This rate at which it changes with x, that is called the derivative, right? So now if I want to calculate what is the derivative of fx at this point, so what I will do, so let's say the value of x is at this point is x, and the value of x at this point is x plus delta x, right? Some delta shift that we do here. So this area, this length is delta x, right? So similarly, if I like take the chain x as 1 and x plus delta x as 2, then delta x would be basically with the difference like 1, 2 minus 1, right? Now, what is the change in fx over here? So here fx is fx, f of this x, right? Whatever the value corresponding to this x. Here, the function value takes is f of x plus delta x, right? Let me. Huh. So the function value corresponding to x plus delta x is f of x plus delta x. So if you compare it with the length example, so here when the x value was 2, function value was 4, right? X value was 1, function value is 1. Similarly, x value is x, function value is fx, x value is x plus delta x, function value is f of x plus delta x. Now the derivative is the slope. The slope is basically this, how fast this is changing. So if you see this red, or let me change the color. So if you see this yellow line, right? So this yellow line represents how fast this fx is changing. So in this case, what you do, you calculate your derivative. Derivative is also written as ddx of fx, that is equals to f of x plus delta x minus f of x divided by delta x, right? So if you see like how to calculate slope of a line, slope of a line is basically the difference in y axis divided by the difference in x axis. So in this case, so tan theta is basically the slope, right? So this length is f of x plus delta x minus f of x, and this length is delta x, right? So it is just the tan theta. So theta is this angle. Tan theta is perpendicular, that is this thing, the numerator, and divided by base, that is the denominator, delta x. So this is f of delta ddx of fx. Now, what you do is to calculate the derivative, you take the limit delta x tends to 0. So this is just what you do is you make this distance delta x as small as possible, so that you get closer and closer to this point where you want to take the derivative, right? So that is the physical idea of derivative. Derivative is just the slope of a line. It just calculates how fast fx is changing, the rate at which fx is changing with x. So for some physical examples, if you must be familiar with speed, the speed of a vehicle or a velocity of the vehicle, right? Velocity of any bike or any car, right? So velocity is basically the the derivative of distance, ds dt, right? V is velocity, s is the distance it covers. So the rate at which uh, the distance you cover changes with time, right? T is time. So the rate at which uh, the distance you cover changes with time, that is basically your speed, right? That makes sense, right? So this is one of the few examples, right, of derivative. So now there could be any functions, right? So the functions could be, you can take any function. So I will also derive for one particular function maybe. So let's take the example as, you know, uh, x square. Let's say your function is x square. Okay. Okay. So, okay. So let's see this formula first. Okay. So I'll just use this formula to calculate the derivative of x square. So let's say your fx is x square. So what is the derivative? dfx dx equals to limit delta x tends to 0 x plus delta x whole square. So you see, you just take f of x plus delta x. First term is f of x plus delta x. So you just replace x with x plus delta x. That will become x plus delta x whole square. Now second term minus f of x. F of x is x square, right? Divided by delta x, right? Now if you solve this, we'll take limit delta x tends to 0. So a plus b whole square is a square plus b square minus 2ab minus x square divided by delta x, right? So this x square cancels, right? So what we are left with is limit delta x tends to 0. So the this thing delta x squared by delta x becomes delta x minus 2x, right? So again, from this term, one delta x cancels with this one, and from this term, this delta x cancels with this. So we are left with minus 2x. So delta x minus 2x. But since we have limit delta x tends to 0, so now we'll make this the first term, this term delta x equals to 0. So we are left with, okay, I think this will be plus. Okay, so I made it minus. Okay. This will be plus because a plus b whole square is a square plus b square plus 2ab. Okay, so one delta x over here, and then we are left with plus 2x, right? So so first term will become 0 because delta x is tends to 0. So the derivative is 2x. So derivative of x square is 2x, right? So this is the derivation. So like this you can derive for all functions, right? So be it the function is e to the power of x, or you know, log x, sin x, cos x, anything. So there are like different charts you can find online, so which shows that given the function, what is the derivative. So I think you actually you can memorize it as far as possible, because some basic functions we should memorize and they may come into use in places, right? So for example, you know, these activation functions are log functions. So for example, soft plus. So soft plus is a log function. So you need to know what is the derivative of log. So like you also have e to the power of x in sigmoid functions. So you also need to know what is the derivative of e to the power of x, right? So these are some of the important derivatives that you should memorize, right? So like log, e to the power of x, and you know, whatever is there being used in the activation function especially, right? So now, for example, as I said, let's see. Okay, so two derivatives that I said is ddx of e to the power of x is e to the power of x. Okay, so the function is itself its derivative. Another is ddx of log x is 1 by x, right? So these things you should remember. Also, ddx of x to the power of any power, uh, any real power, is nx to the power n minus 1, right? So if you see, if you take n to be 2, then you will have x square. So dd of x square would be 2 times x, right? So that's what we got, right? So this is the formula. So if you remember this thing, you can also calculate the derivative of x cube, x to the power 4, and so on, right? Now, coming to chain rule. So these are some simple functions whose derivative you can memorize. But let's say instead of directly giving e to the power of x, you're given something like e to the power of ax square. Right? Then what will you do? So then you have to use chain rule. Right? So what do I mean by chain rule? So if you want to take the derivative of y with respect to x, so what you do? is you assign a different variable to this ax square. So let's say you assign that ax square equals to z. So now what you do is you take the derivative of y with respect to z, and then you take the derivative of z with respect to x, right? So because z with respect to x will be simple, right? So y with respect to z, so this is just e to the power of z. So derivative of y with respect to e to the power of z is e to the power of z times z with respect to x. So z is ax square. So derivative of ax square with respect to x is 2ax, right? So derivative of x square is 2x, and we have the a in front, so 2ax, right? So in that way, then you replace z with e to the power ax square. So you have 2ax times e to the power of x square. So did everybody understand this? So like what happens is e to the power of any function you have. So first you take the derivative of e. Derivative of e is just the same thing. So that is e to the power of x square. Then you take the derivative of the whatever is in the power of e. Ax square derivative is 2ax. So that's one direct way to do it. But this is what this chain rule is all about. Is this clear? So this should be clear because we are gonna use this in backward propagation in detail, right? So yeah, I think you should memorize some basic derivatives, and you should also like if you are not comfortable with this chain rule, you can practice some derivatives on your own, right? And then you'll get more familiar with it, right? But yeah, but let us go back into back propagation algorithm, right? So as I was saying that in the forward propagation we saw how to calculate the um, output if you are given the weights. Now back propagation talks about how to calculate the weights itself, right? The weights you don't know uh, from the beginning, right? So now back propagation is all about how to calculate the weights, right? So now, if you remember gradient descent algorithm, when we are doing linear regression and all those things, so it is very similar to gradient descent algorithm, right? So if you remember, what was the what did we calculate in the gradient descent algorithm? We calculate the least square error, right? So that is exactly what we are going to do. So we are going to calculate the sum of square residuals, right? So it is same as the least square error. It's just the uh, y predicted minus y observed whole square, right? Summation over all the examples, right? So what we do is that to start with back propagation, we uh, uh, randomly initialize all the weights, right, and the biases as well, right? Okay. So my screen is visible on YouTube, right? Okay. Okay, so we randomly initialize the weights and the biases for the first initial run. For the first run, we randomly initialize the weights and biases, and then we iterate and we change the weights and biases until we reach the uh, final value, which gives us the best uh, output, right? So similarly, what we used to do in gradient descent, in gradient descent, we used to initialize our parameters, the slope and all with some random value, and then we iterate it repeatedly until we converge to the minimum error, right? So here also we randomly initialize the weights and biases. So here let's say 2.74 minus 1.13, and this things like random initialization, and then this biases also we initialize. Generally, the biases are initialized as zero value, but you can take non-zero values as well. But conventionally, bias can be initialized with zero value. right? So yeah, so these are our initial parameters that we are using, right? Now what we do is we take all the inputs and we forward propagate them using the first initial weight, right? So let's say our first input is 0, we multiply it with this weight, add it to this bias, and then calculate the output. So we'll get some value of output, right? So whatever value of output we get, then that output might not match with the actual value. So initial input is, let's say, 0. So we have three input values, right? If you see in the previous slide, so we have three input values. One is 0. Second one is this dosage is zero point 0.5. This one is dosage is 1. And for the zero point 0.5 dosage, we desired to get an output of 1, right? So yeah. So initially, let's say we give three inputs. The first input 0, zero point 0.5, and 1. And for the correspondingly, we calculate what are the outputs, right? So first, so we give the input one by one to all the three values. We calculate the output, and the output, actual output, and the predicted output would have some difference. So we calculate that difference and then square it. So so this SSR, the sum of square residuals, is basically observed minus predicted whole square, and then summation over all the inputs. In this case, we have three inputs. So summation over the observed value minus predicted value for all the inputs, right? So that is the SSR. Okay. So when you calculate the SSR for the first iteration, then what you do, then you want to refine the weights and the biases for the next iteration. How do you refine it? So if you remember from gradient descent, what we used to do in gradient descent is that uh, to update the weights or to update any parameters, you would basically take the derivative of the cost function with respect to that parameter, right? So for example, if you are updating, let's say, b3, right? So your error, you take the derivative of the error function with respect to b3, and your b3 in the next iteration would be b3 in the previous iteration minus the derivative of error with respect to b3. So that's how you update it, right? So if you remember, so let me show you. So let's see, I think it's probably in week 2, I guess. Yeah. So here, if you see, so this is the gradient descent update algorithm, right? So theta j in the next iteration would be theta j in previous iteration minus some alpha learning rate of dd theta of the cost function j, right? And that's how you move towards this, uh, the minimum to cost function. This is your loss function, and by taking small steps, you finally converge to the minimum, right? So yeah. So similarly, in our case, in the neural networks, in the backpropagation algorithm, so theta is our b3, or it could be other weights, b1, b2, b3, w1, w2, w3, anything. So that will be those weights in the previous iteration minus some learning rate times the derivative of the uh, SSR with respect to that weight or that bias, right? So this we know, right? So previous iteration, we know what is the value of weights and biases. We just need to calculate what is the derivative of SSR with respect to the bias or the weight, right? So that's what we do, and that is we do using this chain rule, right? So for example, d of SSR with respect to B3 would be d of SSR with respect to predicted times d of predicted with respect to B3, right? So similarly, you can see what are the derivative of SSR with respect to weights, all this W3, B1, W1, right? So now let me just explain like how this comes, how the how using the chain rule we can get to this. So yeah, as I said that your SSR is basically this thing, sum over all the inputs. In this case, you have three inputs, sum over I ones 1, 2, 3, observed minus predicted whole square, right? That's simply the least square error, right? So now what you have in this, if you remember the forward propagation algorithm, you multiply the input with W1 and then add it to B1, right? So here, if you let's assume that let's store it in some variable x1. So x1 equals to w1 into input I plus b1, and then you pass x1 through y1, right? So y1 equals to function of x1. So whatever function, in this case soft plus. So if you pass it through this function, your output you get is y1, and you multiply the output y1 with w3. Similarly, you do this for the bottom channel. So your predicted value would be y1 times w3 plus this y2, this output from the bottom channel, times w4 plus b3, which is the bias in this final node. This is your final predicted output, right? Is this clear? Is this red box clear? So these are just some uh, variables that I have assigned, but this is just the forward propagation algorithm. Till now, I haven't used any backward propagation terminology, right? So if you are good on this, then what we do is we calculate the derivative of this SSR with respect to B3. So let's look at B3 first, then we'll go into W3, W4, and all those things. So for to calculate the SSR with respect to B3, what we do, so if you see this SSR is not directly a function of B3. So this is a function of observed and predicted, right? And the predicted is in turn a function of B3. If you see over here, this equation, this predicted is a function of B3. So if you remember from the chain rule, what we do is take the derivative of SSR with respect to predicted and then take the derivative of predicted with respect to B3. So that's what we had done. So first take the derivative whichever is a direct function and then take the derivative of this function with respect to B3, whichever is a direct function of over here, right? So SSR with respect to predicted is just the derivative of this whole squared term, right? So observed I is basically a constant term, right? So this is constant because this is a fixed value. Observed value is the value that is given in your data. It's a constant number. So in this case, for the I equals to 1, which is dosage 0, that is the observed value is 1. Sorry, 0 basically. The because the medicine doesn't work. For I equals to 2, the observed value is 1 because the medicine works for dosage zero point 0.5. Again, for I equals to 3 for dosage 1, the observed value is 0 because the medicine doesn't work, right? So observed value are like fixed numbers, 0, 1 in this case, and predicted value would depend on B3, right? So you first take the derivative of SSR with respect to predicted, then take the derivative of predicted with respect to B3. Now, to look at the first part, derivative of SSR with respect to predicted, so this is similar to x square derivative, right? So what we do is again we apply chain rule. So x square derivative is 2x. So 2 times observed minus predicted, and then we take the derivative of the inside part, which is this is constant, so derivative is 0, and the derivative of predicted with respect to predicted is basically 1, right? Okay, so yeah, so that's what we did over here, and then take the derivative of predicted with respect to b3, right? So actually in this case, if you see here, I think I made a mistake over here. So because there will be one negative sign that will come outside, right? So derivative of, if you take the derivative of the inside part, so the derivative of observed is 0 because it's a constant. Derivative of minus predicted, so this minus would come outside. So here you would basically have a negative sign in the minus, right? So this negative sign from the minus predicted, right? So this will come over here, and the derivative of predicted with respect to b3. So again, these terms are not dependent on b3, so these are constant. So this will become 0. This will also become 0. Derivative of b3 with respect to b3 is just 1, right? So this is the final derivative of SSR with respect to b3, right? Similarly, you calculate the derivative of SSR with respect to W3. Okay. Again, d of SSR with respect to d of predicted. Here again, I missed the minus sign. Okay. So d of twice observed minus predicted. So this is the same thing. And then times d of predicted with respect to W3. Right. So from this formula, if you see what is the derivative of predicted with respect to W3, so this is W3. So the derivative will be Y1, right? So this is the derivative, right? Similarly, you calculate the derivative with respect to W1 and W1, W2, B1, B2. So W1 would be a little more complicated because here you need to take the derivative of this Y1 as well. And Y1 is a function which is a soft plus function. So you have to take the derivative of the soft plus function. That's why you need to know the derivative of log and those things, right? So let me go through this once. So derivative of SSR with respect to W1 would be derivative of SSR with respect to predicted, and then derivative of predicted with respect to Y1. Why? Because this Y1 has W1 indirectly, right? So Y1 is a function of X1, and this X1 is in turn a function of W1. So you see, there are a lot of chains. There are like two, three chains that you have to go through, right? So, so there is no direct function. All the things are an indirect function of one after another. So you have to follow the chains and you have to take the derivatives as you follow along. So SSR is directly a function of predicted. You take the direct function derivative first, and then predicted is directly a function of y1. So you take the derivative of y1, and then y1 is directly a function of w1, right? So you take the y1 is directly a function of x1. So y1 is a function of x1, and this f is basically the soft plus function, right? What we take. So d of y1 by dx1, and then x1 is a function of w1. So d of x1 by dw1, right? Take the derivative of x1 with respect to w1. So the first part is again, I missed the minus. Okay, so there will be minus twice this thing. This we have done. Derivative of predicted with respect to y1. So if you take the derivative here, you'll get w3. Derivative of y1 with respect to x1. So y1 is, you see, is a function of x1, and this function is soft plus function, which is log of 1 plus e to the power x, right? So if you see here, you need to use the derivative of log. So log of 1 plus e to the power x is 1 divided by e to the power x times the derivative of the inside part, inside of the log. So inside of the log is e to the power x, derivative is e to the power x. So the total derivative comes out to be e to the power x divided by 1 plus e to the power x, right? So think about it this a bit. If you are not very familiar with derivatives, think of like how does log of 1 plus e to the x comes out to be this, right? So maybe practice a bit more. And then finally, d of x1 with respect to w1. So d of x1 with respect to w1 is just input 1, right? Input I. So yeah, again, like if you see, all these are assuming that derivative of any constant times x is basically that constant, right? So yeah, you should be familiar with this. So for example, here, if I am taking derivative of x1 with respect to w1, so here the constant is input I, right? And my x is w1. So input times w. So here input times w, the derivative is the input, right? The c constant is the input. So that's how you got this, right? So yeah, you should be familiar with these derivatives. And yeah, here I have calculated the derivative of y1 with respect to x1, right? So this is how you calculate the derivative of SSR with respect to W1, W2, W3, W4, B1, B2, B3, and so on, right? Using this chain rule. Finally, after you obtain these derivatives, you update the parameters b3, b1, b1, b2, b3 like this, like the gradient descent that we saw, right? This is just the learning rate, the eta, and this derivatives you calculate, right? Okay. So I think I did for one example, like if input one is zero for the input one, the observed value is basically zero, right? Because it is not, uh, it is showing result zero, right? So you forward propagate it, you get the output which is 0.68. So forward propagate using what we did earlier, and then you calculate the SSR of with respect to BC. So you can do these calculations for uh, each of those inputs, and then you know. So all these SSRs will have a summation of with respect to I in front, right? I have not written the summation, but there will be a summation in front of each of them. So whatever the number of input parameters, in this case you have three inputs, so you have to sum over all the three inputs, sum over these values for all the three inputs, right? So this is how you calculate the derivative, and then you update this weights. So you go on updating these weights until you converge to a value, so that after this iterations your value of the weight doesn't change by much. So you converge to that weight, and that is your final weight that you will get. And in this case, your final weight turns out to be these values that I have shown here, right? So this is after lot of iterations of back propagation that you arrive at these values. And initially you start with these values, right? So after you initially start with these values, after a lot of iterations, you end up at these values, right? So is there any question? Week 7 assignment. Okay. Okay, let me see. What is the question number? Do you have the question number? Okay. Yeah, third. Okay. So suppose you have inputs um, x, y, z with values -2, 5, and -4 respectively. You have a neuron Q and neuron F. Graphically represented the functions is as follows. What is the gradient of F with respect to x, y, and z? Okay. So yeah, let me do it in my notebook. Let's see. So let me draw the neuron first. Okay, so what it is saying is that uh, you give these inputs x, y, and z, which has values, fixed values, -2, 5, and -4. Yeah, and these x and y's are being passed through this q node, right? So they are being summed up. So q node is basically summing up x plus y. So x plus y is summing up means 5 minus 2. So it is giving us 3, right? And then what is happening is f, this second node. So what it is doing, second neuron is basically multiplying the output value of q with this z value, right? So output value of q is 3 and z value is uh, -4. So 3 times -4 is -12, right? And then maybe it is passing it through some, sigmoid function or something like that. And if you remember the sigmoid function, so uh, let me go back to the whiteboard now. So yeah, so so if you remember, the shape of the sigmoid function somewhat looks like this, right? So this is 0. So -12 will lie somewhere over here. So the output of the sigmoid function corresponding to -12 will be basically be almost close to 0, right? So sorry, close to yeah. Okay. So whatever. So let's say the function is giving out output to be -12. So basically q times z. So 3 times -4 is -12. Okay. So now they have asked to let me see what have they asked. Huh. So now they have asked what is the gradient of f with respect to x, y, and z. Okay. So let's write down the functions that are. Let me come back to my whiteboard now. So let's write down the functions that are over here. Okay. So for example, q is basically given as x plus y, right? And f is basically q times z. Okay. So this you can simplify, that q is x plus y times z, right? So f will become x plus y times z. You can also simplify it as a xz plus yz, like this. Okay. So now you have to calculate simply the derivative of f with respect to x, y, and z. So as I said, the formula is, if you take any function, so let me do it this way. So derivative of cx with respect to x is c, right? So where c is a constant. So if c is a constant, so then derivative of cx would be c. So if you remember this, with the help of this, you can calculate the derivative, right? So similarly, df dx. So you take the derivative of d dx of xz plus d dx of yz, right? So for the first term, if you see, you can treat z like an x, right? Sorry, z like an c. So if you compare this formula with this, right? Here, the c is acting like a z. So here you have cx, here you have zx. So the derivative would be z. And this term doesn't have any x. So this will be 0. So the derivative would be xz, right? Similarly, you can calculate the derivative with respect to uh, y and z, right? Okay. So this is what you have to do, right? So df dy would be again ddy of xz plus yz. So the first term xz doesn't contain y, so the derivative would be 0. So the second term ddy of yz is similarly z. Sorry, ddy of yz is, yeah, z, right? Similarly, df dz. So dtz of xz plus yz. So from the first term, the derivative you get is x. From the second term, you get y, right? So the derivative would be x plus y, right? So let's see if you have any options. Yeah. So I guess you have to sum them up, right? So basically, from the value you have been given, so z value is given out to be -4, right? And y is, yeah, -4, x and y value. So x plus y would become 5 minus 2 3, right? So derivative would be uh, -4 3, right? So -4 3 c, right? Is that okay? Okay, is there any other questions? So practice this things. Maybe you have to memorize some of the basic derivative formulas. So I gave you some of the basic formulas like derivative of cx. So this is one of the important formulas that you have to remember, and derivative of log, and e to the power x. Those things you can remember, and you know, then you can work with those. So instead of this plus function, they could have given some other functions as well, right? So after this plus function, let's say you pass it through a some activation function, some log of something or e to the power of something, then you have to take the derivative of that activation function as well, apply chain rule as well, right? So if you remember from what we explained in the back propagation algorithm, you might have to do those complicated steps as well, right? So those could be given in the exam, right? So I suggest you practice this chain rule and the how to take derivatives, and memorize some basic derivative formulas. Those will be helpful. I mean, chain rule you can practice it like uh, without without having to do anything with machine learning. Those you can practice from Google or anything. You can find lots of problems online. So practice those things, and then I think it'll be easier. Okay, is there any other question? Is there any question from this week, like week 8? Did you go through the lectures on clustering, those things? I will cover those part. Uh, I will cover the clustering part in the next week. So yeah. So on Tuesday we will have our regular classes as well. There I will cover clustering. But yeah, you can ask if you have any questions from the lectures or the assignments. Some questions on probability week 4. Yeah, let me go to week 4 then. Okay. Yeah, which question? Okay, Ramesh is asking when will we use RNN? So RNN stands for recurrent neural networks. So I think in the lectures the professor didn't cover RNN in much detail. So from an examination point of view, I guess it's not very important. But uh, I I mean, in my you know in my week 6 lecture, if you can go towards the end, so there I have covered RNN. So in short, when to apply RNN is when you have some time series data, or you know some sort of data which you give continuously as input, which you need to give continuous input to the model, right? So then you need to use recurrent neural networks. RN stands for recurrent neural networks, and the recurrent, the term itself, it means that you're giving the something as input continuously, like recurrently you are giving, right? That's where you need to use RNN. So for example, if you see in this diagram, so you are giving a time series data, like you are giving input x at time t minus 1, then t, and then t plus 1, right? And then the model is performing. So yeah, so I have done one hands-on example on how the RNN works in week 6. So there you can get the details. But to answer in short, when to use RNN is when you have some continuous data that you want to feed to your model. Then use RNN. Okay, so on probability, which question from week 4? Do you have any particular question in mind? Uh, Most of the questions regarding Bayes theorem. Okay, I can explain one question. I think that will be the. Uh, so I'll explain Bayes theorem and then I will explain one example. Which one do you want me to do? Question 4. Okay. So this is like Bayesian network question, right? So if you remember, uh, I had done one example on Bayesian network as well in the week 4 if you go. So if you look at this example, I think right. So yeah. Okay. So let me. So you understood this example, right? So then I will just explain for that one. Okay. So yeah. So here you see. So for example, uh, here wet grass depends on rain and sprinkler. So you can draw this table from the values that are given over here, right? Right. So for example, uh, if I compare this with this, so here you see on time depends on bus late and overslept, right? So you can draw a similar table like this. If bus late is yes, overslept is yes, then the probability of on time yes is this, on time no is this, and similarly like this. Okay, so let me uh, draw a table like this for this example, right? So let me do one thing. Okay. Okay. So what you have is uh, you have rain and sprinkler. So let me first draw the nodes over here. Okay. So you have rain and sprinkler. So let's draw the table for rain. So for rain, probability of yes and probability of no. Similarly for sprinkler, probability of yes, probability of no, right? So uh, for rain, it is given probability of yes is zero point 0.1, right? So zero point 0.1. So probability of no would be zero point 0.9, right? Similarly for sprinkler, probability of yes is zero point 0.2, probability of no would be zero point 0.8, right? Now you have to see like rain and sprinkler. So in the exam, the main thing is, you know, uh, you have to construct this table from the uh, data that is given, right? So after you construct this table, 90% of the work is done. Then you can easily calculate whatever is asked in the question, right? So yeah, so then it has been given. If rain is yes, sprinkler is yes, probability of wet grass is zero point 0.8, right? So rain, sprinkler, yes and no for wet grass, right? So if you see this table that I am going to construct now is similar to this table, like bus overslept of and then on time yes and no, right? Try to relate it with this table. Okay, so rain, sprinkler, both yes. What is the probability of wet grass? Okay, so rain, sprinkler, both yes. Probability of wet grass is zero point 0.8, and probability of Not weight grass would therefore be zero point 0.2. Zero point 0.8 is yes, 1 minus zero point 0.8, okay, zero point 0.2. Next is rain yes, sprinkler no. Okay, not sprinkler. This is the symbol for not. So rain yes, sprinkler no. What is the probability of wet grass? 0.7. What is the probability of no wet grass? 0.3. Right? Similarly, next is no rain, sprinkler yes. Okay? So no rain, sprinkler yes. Probability of wet grass? 0.6. 6. I hope my screen is visible in YouTube. Okay. Okay. So yeah. So wet grass 0.6, no is zero point 0.4, 1 minus zero point 0.6. Now the last one. Probability of wet grass, no rain, no sprinkler. So both no. Okay. So no, no. That is given at zero point 0.5 probability. Probability of no wet grass is 1 minus zero point 0.5, zero point 0.5 again. Okay. Right. So this is how you construct the table. So now you got the table similar to what we had got. Right. Now you tell me like how will you solve this P of S with respect to W and R? Can anybody tell me? Okay. So you have to calculate P of S given W and R. So probability that sprinkler was on given that you have a wet grass and you have rain, right? So that will be okay. Who can tell me? Now, if the question was probability of wet grass, given that you have rain and sprinkler, like if it had been reversed, right? So let's say the question is like this: probability of wet grass given sprinkler and rain. What will be the answer then? Probability of let's say no wet grass. No wet grass then 0.2, right? Right. So similarly, from this table, you can calculate uh, these things. Now you have to calculate the other way around. Probability of sprinkler given wet grass and rain, right? Okay. So if you remember Bayes theorem, so what was Bayes theorem? Let me write it over here. Bayes theorem is P of A given B equals to P of A and B divided by uh, P of B, right? Sorry. Wait a minute. Yeah, so that was the conditional probability P of A intersection B by P of B. Similarly, P of B given A could be written like this: P of A intersection B divided by P of A. Now you multiply these things, then you have P of A given B equals to P of B given A times PA divided by PB. So this is Bayes theorem. Okay, right? And these are the formula for conditional probability. Right. So this is formula for conditional probability. So let's use this one then. So P of S given WR is P of S intersection W intersection R divided by P of W intersection R. Right. So what does it mean? It means that probability that sprinkler is on and it had wet grass and it was raining, all are true, divided by probability of wet grass and rain. Okay, now that's why I introduced you to another theorem or another law called the law of total probability, right? So what did law of total probability talks about? So if you don't remember, you can go back to the week 4 lectures, and but I will just state here what that law is. So basically, if you remember, like I was talking about how to divide a whole problem into small chunks, right? To simplify the problem, right? So in which cases P of W intersection R could be uh, true, right? So the denominator, it could be written as intersection R intersection you have sprinkler on plus R intersection sprinkler not on, which is represented by S bar. So not S basically, right? So if you remember, so let me write it here: law of total probability, or let me go back to the slide once. Right. So this is the law of total probability. Remember this. So here, if you are to calculate the probability of some event, you have to see the probability that that you have to look at each of the sample spaces. So given S1, probability of A times probability of S1 plus given S2, probability of A times probability of S2 and so on, sum over all the subsamples, right? So here, in our case, the subsamples are either sprinkler is on or sprinkler is off. So you have to see both the probabilities and add them, right? Or in other way, you can see that probability that wet grass and rain is happening. Okay, both are true. It could be true that either sprinkler is on or sprinkler is off. So what is the probability that we get W and R with sprinkler on, and what is the probability that we get W and R with sprinkler off? That's only two possibilities, right? So now, let me, okay. Now, uh, now we have to calculate these values: S intersection W intersection R and W intersection R intersection S bar. Okay. So as I was saying, if it was the other way around, like if you know you are given W with S and R, you could have calculated. But now you have to calculate S given W and R. So you use Bayes theorem here. where you need to use Bayes theorem. So you see, if you know B given A, you can calculate A given B. So the other way around is easier. So B given A is easier. So you calculate B given A and then you calculate A given B in terms of B given A. Right? So that's the strategy that we are going to follow here. So for this, what we do is, so let's see. So W given S and R, that we know. What is the value? Probability of wet grass given sprinkler and rain, 0.8. Okay. Now we can calculate W. So what is probability of W given SNR? This can be written as, again, using conditional probability, intersection R divided by P of basically SNR, S comma R. But since these are independent events, sprinkler and rain are independent events. So for independent event, what we can do is P of SNR we can write as P of S times P of R. So S intersection R. So again, for independent events, this is a formula that again we had discussed in week 4, right? So we also know P of S, we also know P of R, right? So we just have to calculate. We can get the numerator from here. Okay. So let me see. So this we know, P of S we know, P of R we know, P of W given SR we know, right? So what we can calculate is we can calculate this, right? So tell me what is the value? W intersection S intersection R would be zero point 0.8 times 0.1 times 0.2, right? That will come out to be 0.016, right? So now we have calculated this term. This term is 0.016. This is also the same term, 0.016. Now we have to calculate this term, right? So let's see which one is the easy way. Easy term is P of, again, we know W given not S and R. What is the probability? From the table, read me this value. Wet grass given not sprinkler and rain. What is this value? 0.7. Okay. So 0.7. And then again, simply we expand this and we write it as using the sorry, there is no bar here. Using conditional probability, W intersection S bar intersection R divided by S bar times P of R. So again, we know these values, these circled values. We have to calculate this value, right? We can do this. So this will become intersection S intersection R equals to P of W given S bar intersection R times P of S bar times P of R. So what are the values? 0.7. P of S bar, which is not sprinkler, is 0.8 over here. 0.8 times P of R is zero point 0.1. So that will come out to be 0.056. Right? Okay. So now if you see what we initially need to calculate, we need to calculate this thing. So we obtained this thing, and this thing. Now we just apply it. P of S given WR equals to 0.016 divided by 0.016 plus 0.056. So whatever value you get, that is your answer. Right? Let me calculate this quickly. So this is coming out to be 2 by 9 was 2.22. Right? Is that fine? So answer is C.22. Okay? So you have to see like which uh, terms are easy to get. Like if the reverse term is easy to get, so for example, P of you know wet grass given S and R are easy to get, whereas P of S given WR is difficult to get. So you express it in terms of the other thing, and then from there you know get it. Also, you can try it by using directly Bayes theorem. This can be done in other ways as well, I think. Let me see if I can find another method to do it as well. I will actually let you know if I will post the notes if I find some other ways as well. So I think that will be easier for your understanding as well. So, yeah, but I think did everyone understand this method? Yeah, it is. So I'll think of some easier way. But the main idea here is that uh, if you are uh, you know if you want this thing S given WR, you have to express it in terms of uh, the other way, so that like you get the easier thing. So W given SR is easier to calculate. So you want to express this term in terms of W given SR. So that is how you do it, right? So you have to like practice, maybe practice a few more examples, right? For example, you can take this example which we did over here. So here we calculated bus probability of bus on time given overslept and bus late. Sorry, probability of on time given overslept and bus late. Now try to calculate that probability of overslept given that on time and bus late. So these are some of the examples that you can do and practice. Uh, okay, and then I think you will be better, right? So similarly here, if you are given like probability of overslept given bus late and on time, So you have to see that probability of. Uh, so I will quickly, maybe show it. So maybe in a place. Okay. So yeah. So the first node was alarm on or not. Then you had overslept. Then you had on time, and here you had bus late, right? So this is easy to calculate. On time given, overslept, and bus late, right? This is easy to calculate. This you know. Now you are given probability of overslept given on time and bus late, right? So what will you do? You take probability of overslept intersection on time intersection bus late divided by probability of on time intersection bus late, right? So this again you can divide into on time bus late and maybe overslept and not overslept. So this you divide into P of on time bus late overslept plus P of on time bus late not overslept, right? And then from here you have to calculate the same way, right? So I think it will be better if you practice this, but this is just one example that you can do, and it will take some time, but I think it's a good practice, right? So yeah, and there is actually another one more parameter which is alarm on, right? So yeah, so you have to like also see like what is the uh, thing over here. So like overslept, and you have to add that also here, like if alarm is on or not. So overslept, and let's say you give here alarm on is yes. Here also you give alarm on. So you have alarm on another parameter, right? So your intersection alarm on, right? So this will be alarm on, right? So yeah, actually here you will have more terms, right? So overslept alarm on, not overslept alarm on, plus you will have on time bus late overslept not alarm on, and probability over on time bus late not overslept not alarm on, right? So the bottom denominator will be a summation of these four probabilities, right? So again, you have to apply this law of total probability over here. Okay. Okay, actually not alarm is not given here. So these two terms will not be here because here you have been given alarm, right? So if you had not been given alarm, so then you have to take these two terms again. Okay. If alarm was not given over here in the condition. So if alarm on was not given in the condition, that means alarm could be on, could be off as well, right? So then you have to consider these two probabilities as well. But since if alarm on is given in the condition, then you have to consider only the cases with alarm on, right, in the denominator. Okay. And in the numerator also, similarly, you have to consider if alarm on was given, then you can only consider this term. But if alarm on was not given, then also you have to consider another term, not alarm on. So this term you have to consider one additional term if alarm on was not given, right? So then again you have to calculate the things. Okay, so this will be more time taking if you know larger number of branches are given, but you can practice for at least three branches. Okay, for fourth practice with at least three nodes, right? That will be easy. Okay, so if there are no questions, other questions on Bayes theorem like this: P of A given B, P of A given B bar, compute the value of P of B given A, right? So similarly, you can use Bayes theorem on this, right? So for example, yeah, Monica is saying question 4 in week 2. Okay, just a minute. So let me just say over here. So you can, you know, do it using Bayes theorem only, right? So for example, P of B given A is P of A given B times, uh, P of B divided by P of A. Okay. So P of B given A is P of A given B times P of B divided by P of A. So P of A you can calculate as P of A given B plus P of A given B bar just by conditional probability. Sorry, it's law of total probability. But you cannot calculate P of B. P of B is not given. So that's why not enough information, right? Okay. Similarly here you see P of C given F, P of C given F bar, P of F is given. Find P of C, right? So P of C would be P of C given F. Uh, uh, yeah, wait a minute. Yeah, so P of C would be P of C given F times P of F plus P of C given F bar times P of F bar, right? So zero point 0.8 times P of F is 0.1 plus zero point 0.3 times zero point 0.9, right? And P of F given C, you apply Bayes theorem. P of F given C is P of C given F times P of F divided by P of C. Okay. Okay. Question 4 in week 2. Where is our hypothesis is this? The training data is given in the table. The cost function is this. What is the value of j theta when theta equals to 1 1? So theta equals to 1 1 means theta 1 is 1. Right? What is the value of cost function? So 1 divided by 2m. M is the number of samples. Here you have 4 samples. Right? And then you have to find theta naught plus theta 1x. So theta naught is 1. 1 plus 1 into x. That is 10 here. So 1 plus 1 into 10. That will give you value 10. Sorry, 11. 1 plus 10, 11. So your h theta for this sample is 11 minus yi. Here it is 5. So 11 minus 5, 6 whole square plus you do the same thing for the next three examples, right? Is that okay? Or do you want me to explain it more? Okay, let me see. 10, 5, 3, 3, 6, 7, 8, 6. Okay, so you have been given this. I hope this is the right thing. 8, 6, 6. Okay, so these are the value of x and y that you have been given. Okay, these are the value of x and y that you have been given. Your hypothesis is given out to be 1 plus 1 into x. So for the first sample, your hypothesis is 1 plus 1 into 10, 11. Second, 1 plus 1 into 3, 4. 1 plus 1 into 6, 7. 1 plus 1 into 8, 9. So these are the value of the hypothesis in all the respective cases. Now your j theta is 1 divided by 2m. 2m is the total number of samples. 2 into 4. Here you have 4 samples. 1, 2, 3, 4. Now summation over h theta minus y whole square. That is 1 by 8 times. Now summation, I will sum over each term. 1, 11 minus 5 whole square. So h theta is 11 for the first case, y is 5. 11 minus 5 whole square plus 4 minus 3 whole square. This 4, this 3. 7 minus 7 whole square. Okay. So on. Plus 9 minus 6 whole square. Right. So this is what you have to calculate. This is okay now. Okay. Yeah, this is what you need to calculate. That's it. Okay. Okay. So we will end this call and we will meet again on Tuesday as usual for week 8 lecture on clustering. And till then, uh, yeah, see you. Okay. Yeah. Bye bye. Good night. Thank you, everyone.